Hello, welcome to our talk on UGEMM, Unary Computing Architecture for GEMM Applications. And here is the speaker, Di. In this talk, we have three goals. First, we review the demands of energy-efficient GEMM implementations and motivate UGEMM over other Unary approaches. Second, we demonstrate UGEMM's capability for arbitrarily encoded input for multiplication and addition mathematically. Third, we prove the knob of UGEMM's high energy efficiency to be early termination enabled by high accuracy and stability. To begin with, let's review some background knowledge first. General matrix multiply is ubiquitous in applications like computer vision, signal processing, machine learning, and so on. Moreover, it's at the center of deep learning. According to profiling, 95 and 89% of GPU and CPU runtime are devoted to GEMM operations, indicating that the energy efficiency of GEMM is critical for emerging applications. Unary computing proven to have higher energy efficiency than conventional binary computing can act as salvation. Next, let's review the differences between binary and unary computing. Binary computing contains both bit parallel and bit serial designs. The bit parallel design uses spatially distributed parallel bits with varying significance. On the other hand, the bit serial design compute bit serial bits spread in temporal domain. Then unary computing operates on serial bits with equal significance, also in temporal domain. For example, a unary addition needs 16 cycles to finish. For unary computing itself, there also exist two major schemes, including stochastic computing and race logic, both using bit streams as data. Stochastic computing utilizes rate-coded data, which means the probability of ones matters. And the bits are generated randomly by comparing the source binary data with a random number from a random number generator at each cycle. On the contrary, the race logic applies temporal coding for the bit stream, where the delays of ones matters. Those bits are generated deterministically by comparing the source data with a number from the counter per cycle. Besides the encoding scheme, the bit stream also has different polarities, including unipolar and bipolar. Both polarities has the same unary bit stream length under identical binary bit width. Given the probability of ones as P1, unary bit stream has value of P1, referring to unsigned data ranging from 0 to 1, while bipolar bit stream has value of 2 by P1 minus 1, corresponding to signed data of range between -1 and 1. After the basic format of unary bit streams, I also going to introduce two metrics to measure the bit stream, namely their correlation and stability. The existing correlation measures how two bit streams are similar to each other and will influence the final accuracy of unary computing. For example, +1 is the maximal correlation, meaning the count of aligned ones is maximized. This is expected in temporal coding. Then zero correlation means a balanced count of aligned ones, which is desired in rate coding. Finally, -1 correlation refers to the minimized count of aligned ones. The second metric, stability, is a new metric designed in this work to measure how fast a bit stream converges to the expectation. For example, given a bit stream, the error versus cycle is presented in the diagram. Then it's easy to identify whether the output error is bounded by an error threshold as the gray line. Therefore, we define the stable point as the cycle from which the error never exceeds the given threshold, and the stability as a ratio of stable cycle count to the total. The stable point in this example is cycle 7, and the stability is 0.625. Then for another bitstream of the same value, it has earlier stable point at cycle 4 and a higher stability of 0.8125. The takeaway for this new metric is a higher stability enables earlier termination for unary computing. After above background, I will introduce the motivation of our work. Our proposal is a unified unary computing architecture for GEMM, which is the first to support addition and multiplication in temporal coding. Next, we hope UGEMM to have the compatibility for inputs with varying codings and polarities. Furthermore, early termination is also considered in UGEMM for ultra-high energy efficiency, which is enabled by two factors. First, the computation can be done in a fully streaming manner, eliminating the data buffering as in other designs. Second, UGEMM's high accuracy and stability is also essential for the reliable early termination. In the following, I will present the UGEMM microarchitecture and architecture. Here is a list of the involved microarchitecture designs, including both matrix multiplication and addition. The addition has two versions, scaled and non-scaled. Both polarities are supported in UGEMM microarchitecture, among which bipolar non-scaled addition is first supported ever. In the following talk, I will use unipolar versions as examples to explain how UGEMM works. First, let's check the multiplication. The expected multiplication result is the product of input values, denoted as V. For unipolar, the value equals to the probability of 1's p. Conventional unary multiplication uses an AND gate. However, the actual AND gate function contains a conditional probability instead of the marginal probability. When the conditional probability equals the marginal probability, the correlation between two bitstreams is 0, and the multiplication is accurate. Otherwise, the correlation is non-zero, and the product is erroneous. To bridge the gap, we use conditional bitstream generation to enforce the equivalence between the two probabilities, therefore enforcing zero correlation, which is not possible in other designs. The implementation is simply using one of the AND gate input to control the generation of the bitstreams to another input of the AND gate, with the overhead of one extra enable signal to the random number generator. A walkthrough example is provided here with both input of value 2/4. Note that the value of input 1 is statically stored in the counter as 2. At the first cycle, the counter value is larger than the random number 1. A logic 1 is generated by the bitstream generator and sent to the AND gate, labeled as blue. Together with the logic 1 in the input 0 to the AND gate, logic 1 is output. At the second cycle, the random number generator is updated to 3, as in previous cycle, the enable signal is logic 1. However, now the counter value is smaller than the new random number, 3. A logic 0 is generated for input 1 to the AND gate, leading to output logic 0. In the third cycle, there's no signal change from the second cycle. AND gate output a logic 0. In the fourth cycle, though input 0 is logic 1, the AND gate input 1 remains logic 0, leading to logic 0 as the AND gate output. Finally, let's check the result. 1 out of 4 bits are logic 1, so leading to correct multiplication. After multiplication, let's move to addition. I will start with a walkthrough example for scale addition, which essentially calculates the mean of inputs. In this example, 4 values are provided with their bitstreams. The PC is parallel counter, used to count the number of 1s in the input. SA is the accumulator whose carry bit is the addition output. At the first cycle, there are 4 logic 1s. Thus, the PC is of value 4, and the carry bit of the accumulator, also the output, is logic 1. At the second cycle, the residual in the accumulator is cumulated with the current PC value. Due to no carry bit overflow, the output is logic 0. In the third cycle, output is still logic 0, though the accumulator is updated to 3. In the fourth cycle, the accumulator has a valid carry bit and output logic 1. Among total 4 cycles, the output has 2 logic 1s out of 4, indicate correct scale addition. To sum up, we formulate the scale addition of values as the summation of the count of logic 1s, and a carry overflow mechanism is used in scale addition, which is the input counting process followed by the carry overflow process. Then, in non-scale addition, the computation is clipping the sum of input to legal unipolar or unary data range between 0 and 1 here for unipolar. We use the identical inputs as those in scaled addition. At the first cycle, the parallel counter sum up all logic 1s and store their sum in accumulator 1. The offset value is 0 for unipolar non-scale addition and is ignored in the table. Thus, we can consider the accumulator 1 as a storage for the anticipated number of output 1s. The accumulator 3 records the historical output logic 1s and is 0 at this point. As accumulator 1 is now larger than accumulator 3, current output is logic 1. In the second cycle, the accumulator is directly accumulated with the current input count. Accumulator 3 is updated to 1, but still smaller than accumulator 1. Thus, output is logic 1. The same holds for the third and fourth cycle. Finally, the output is 4 logic 1s out of 4 bits, exactly the clipped additional result. Similar to scaled addition, we can also formulate the non-scale addition of values as the count of logic 1s. And the output tracking mechanism is applied to decided output, which simply checks the difference between the anticipated and historical output logic 1s. Based on above microarchitecture design, the processing element is given here on the right. Due to the small size of unary computing unit, one PE can process multiple MAC operations simultaneously. More importantly, this PE is input insensitive. First, the multiplication generates the operand conditionally and mitigate the accuracy loss due to correlation. Second, the addition only cares about the bit count and mitigate the accuracy loss due to different bitstream distribution. By arranging multiple PEs as in this diagram, UGEMM architecture is achieved. Input A is broadcasted to all PEs in the row. Input B is broadcasted to all PEs in the column, while each PE takes one C element. With such arrangement, each PE calculates one output element, significantly reduce the data movement in binary computing, and reaching the high parallelism due to low-cost broadcasting. Next, due to the PE design, UGEMM is also input insensitive. Finally, as UGEMM is input insensitive, it can enable reliable early termination. This feature is powered by 2 factors. The first factor is that the fully streaming computation due to input insensitivity. UGEMM can digest output from another UGEMM instance with high accuracy, performing consecutive GEMM operations without buffering. The second factor is the high accuracy and stability. without which the early termination can never meet the application demands in terms of accuracy. We will show the accuracy and the stability performance in the following. Let's first check the unipolar multiplication performance. For multiplication, we have 4 designs, among which the AND gate and the AND-MUL and NMUL in gray are existing designs. The UMUL ST statically store the input in the counter, while the UMUL IS dynamically counts the input logic ones working in a streaming manner. The accuracy diagram on the top row indicates high final output accuracy of our design. Then the bottom diagram represents the output to input stability of different designs, which indicates the ability of the computing unit to maintain the input stability. A high stability implies that we can early terminate the computation for this computing unit. Our UMUL ST always shows the best among all. Furthermore, both rate-coded and temporal-coded inputs are fed to those designs. Our design exhibits minimal variance in both accuracy and stability, implying its input insensitivity. Then let's move to addition. Both scaled addition and non-scaled addition performance are presented as on the left and the right, respectively. Similar conclusions can be derived: accurate final result, faster stabilization, input insensitivity. Note that our non-scaled addition is the first to support bipolar. This slide shows the performance of the UGEMM. We evaluate all possible configurations, including the polarity, encoding scheme, addition scale. Compared with existing GEMM implementations, UGEMM provide most accurate final result among all. Second, UGEMM also has reliable early termination, which means earlier stable point. Let's draw a vertical dashed line through the stable point of bipolar scaled UGEMM with rate-coded input. And all the stable points from other designs significantly lag behind. This translates into the fact that given a target accuracy budget, UGEMM needs much less cycles. Finally, UGEMM is the most input insensitive among all, reflected by the minimal difference between the accuracy curve of rate-coded and temporal-coded input. In addition to the architecture level evaluation, we further present the application level performance using a multi-layer perceptron. The cycle level accuracy of 2 designs that support fully streaming computation are presented. The final accuracy of the fully Moine model is over 96. After 8-bit quantization, the fixed point accuracy is also over 96%. UGEMM can then achieve around 95% final accuracy, while GAN's design can only achieve 88%. Furthermore, we also present the cycle count to reach 95 of final accuracy. The UGEMM requires 71 cycles to reach 95% of its final accuracy, while GAN's design asks for 195 cycles, demonstrating the early termination feature enabled by UGEMM architecture. This last slide presents a brief comparison in terms of energy efficiency. Compared to other Unary designs, UGEMM has higher energy efficiency, though slightly higher area. Compared to bit parallel designs, UGEMM reaches 1x and 10x energy efficiency for matrix multiplication and convolution. Compared with bit serial design, UGEMM has 5x energy efficiency for matrix convolution. All above energy efficiency benefits dates back to the high computing density and early termination of UGEMM. This also concludes the talk. Thank you all for listening, and welcome to our online session for questions.